Imagine you are gazing at the beauty of the night sky, and all of a sudden you discover a new big bright star in the sky, which you have never seen before. Day by day, it's increasing its brightness. But after 3 months, you realize the star has vanished. On 1st May, year 1006, people from China, Japan, modern-day Iraq, Egypt, and Europe observed the same in the sky. This was around the constellation Lupus. Out of curiosity, they described it as a gay star. It was visible for 3 months. It was about 100 times brighter than Venus and nearly as luminous as quarter of the moon. Fast forward to the year 1054. On 4th April, one more gay star appeared in the sky. Both are visible during daytime. This time near the Taurus constellation. It was around 4 times brighter than Venus. Now, when we see the same location, we find the remnant of supernovas. The supernova 1054 is very famous for its beautiful Crab Nebula and its active neutron star at the center of the nebula. We have also found evidences of these supernovas in many ancient records. So people have witnessed the nova and supernova long before. But in past days, these guest stars usually increased the anxiety and confusion among people. And now, scientists are eagerly waiting to observe a beautiful supernova. Today, in this video, we will talk about the supernova. Hello everyone, my name is Aditya and welcome back to my YouTube channel, Sky Map. Famous American astronomer Carl Sagan said, "We are all made of star stuff."
We're made of star stuff. We are a way for the cosmos to know itself.
This means every element present in our body has originated from a star. But how? Is it even possible? To know the answer, we have to have some minimum knowledge about the supernova. The word supernova came from the Latin word nova, which means new. It was used to describe a new bright star. In some rare cases, when a star dies, it creates a big explosion. This explosion is called supernova. This can be so massive and so luminous that it can easily outshine the whole galaxy. Usually, the supernovas are 2 to 5 billion times more luminous than our Sun. For example, the supernova of the year 1006 was almost 4 billion times more luminous than our Sun. Our Sun releases a huge amount of energy, but a supernova's each second energy release can be equivalent to the energy release of Sun's entire lifespan, and even more than that. So the supernova event can easily outshine the brightness of the whole galaxy. This kind of deadly explosion can start a chain reaction of destructions in space. But the good news for Earth is there is no such massive star in the destructive range. The nearest massive star that can do supernova is Betelgeuse. It is the second brightest star in the Orion constellation. It's a red giant star with the mass of 14 to 19 solar mass and almost 408 to 548 light years away from us. Some studies suggest it will go through the type 2 supernova process within next 100 to 300 years. On the other hand, some suggest it will take 1000 to 3000 years to explode. If it's only 100 to 300 years away, then the star must have gone through the supernova. It's just a matter of time. as the light is taking time to reach us. Whatever, it's a very small period on astronomy scale. This supernova is not harmful to Earth if and only if there is no gamma ray blast pointing towards our Earth. This will be a memorable event for human civilization because these rare events' luminosity can easily surpass the bright moon in the sky, making it easily visible in a sunny day. So, it's very important to know about supernova, the destruction of creation. There are mainly two kinds of supernova, type 1a supernova and type 2 supernova. First, let's talk about the type 1a supernova. Before starting, let's talk about how stars generate energy. Star generates energy from nuclear fusion reaction. Due to the excessive mass, the gravity of the star creates excessive temperature in the core. Due to this temperature, the main element of the core, hydrogen, starts to fuse and creates helium. This radiation generated due to the fusion reaction comes out from the core and counteracts with the inward gravitational force. When the hydrogen burns out, it starts fusing helium in the core and produces carbon. When the helium burns out, carbon fuses and the fusion goes on. Carbon to neon, neon to oxygen, oxygen to silicon, and at last, silicon to iron. Why last? We will know about it in the type 2 supernova. For better understanding, I highly recommend you to see this video after watching this one. Now, for low mass stars, the mass of the star is not sufficient for fusing carbon. Low mass stars can fuse hydrogen in helium and helium in carbon, but can't fuse carbon in any heavier elements due to insufficient mass and gravity. So, carbon-rich core starts forming in the core of the star. With time, the outer layer of the star starts leaving the host star and creates a planetary nebula, and the carbon-rich core left behind, creating a white dwarf in the center of the nebula. In a white dwarf, there is no counter force against gravity, as there is no nuclear fusion. So, to keep it in equilibrium, the electron degeneracy pressure takes place. It counteracts the inward gravitational force. As a result, the white dwarf comes in a stable condition. In our universe, a binary or higher number star system is not rare. If one star in this multiple number star system is a white dwarf, then it starts a unique process. The white dwarf starts stealing material from the main star. It increases the mass of the white dwarf. But according to the great Indian physicist Subramanian Chandrasekhar, the mass of the white dwarf should have a limit. When the mass of the white dwarf crosses Chandrasekhar limit, means 1.44 solar mass, the electron degeneracy pressure can't hold back the white dwarf. Within seconds, it blasts out with an enormous amount of energy. This explosion destroys the star completely. It's called the type 1a supernova, also known as nova. This type of supernova generally emits the highest amount of light among all types of supernova. From our perspective, we will see a new star in the sky, reaching its highest brightness within 3 to 9 days. After that, getting dimmed and eventually disappear within a time period of 80 to 90 days. There are two things very common among all type 1a supernovas. Firstly, it occurs when the white dwarf star is unable to fuse any elements and completely relying on electron degeneracy pressure. There is no hydrogen present to fuse. So, from the type 1a supernova spectrum, we don't get any hydrogen emission line. Secondly, the luminosity of type 1a supernova always stays near about the same, as the supernova always occurs when the mass of the white dwarf exceeds just 1.44 solar mass. For this unique property, astronomers imagine it as a standard candle to determine the distance in the vast universe. As this kind of supernova always emits a specific amount of light, scientists can calculate the distance from it by measuring how dim it appears from the Earth. By using the original brightness and observed brightness, the distance can be measured easily. There are two reliable methods for measuring the distance from distant galaxies. First one, type 1a supernova, and the second one, Cepheid variable stars. Do you know about Cepheid variable stars and why it is used as a standard candle? If you know, please write it down in the comment section. The supernova that occurred in the year 1006 was a type 1a supernova. Now, let's talk about the type 2 supernova. Before 1987, the knowledge about the type 2 supernova was very limited. But on 23rd February 1987, telescope captured a blast of neutrinos. It was a type 2 supernova in our satellite galaxy, the Large Magellanic Cloud. Scientists have studied the event thoroughly, and till today, the study is ongoing. The famous James Webb Space Telescope released this image of the supernova on 31st August 2023. Unfortunately and fortunately, we don't see many supernovas in our galaxy. In outer galaxies, it's almost one in every 100 years, or even more. It's unfortunate because it gives scientists less opportunity to study a supernova. And it's also fortunate because supernova means destructions, not good for life. Let's see what is type 2 supernova. When a star more massive than 8 solar mass or 8 times heavier than our sun becomes old, it enters its red giant phase. This kind of star generally carries sufficient mass to fuse carbon into neon. Even it doesn't stop there. As the mass of the star is sufficient to create enough gravitational pressure on the core, it further increases the temperature of the core. So eventually the neon gets converted into oxygen, then the oxygen into silicon, and at last the silicon gets fused and produces iron. As the fusion goes on, the radiation coming out from the fusion reaction counteracts the enormous gravitational force of the massive star. So the radiation coming outward from the fusion saves the star from collapsing. If the fusion stops, there is no force against the star's insane gravitational force. The star will collapse for its own gravity. In periodic table, elements lighter than iron releases energy during nuclear fusion. However, heavier elements than iron consumes energy during nuclear fusion. It's called iron peak. So the star's gravity tries to fuse the iron in heavier elements like nickel and cobalt. But this reaction doesn't radiate any energy. Moreover, consumes energy. So the core of the star starts filling with iron. Now the iron core starts acting as a hidden white dwarf star. But the difference is the iron core is still under enormous pressure of the whole star. For this reason, the core starts generating energy from electron degeneracy pressure. In simple words, due to the star's insane pressure, the orbital radius of the outer electron gets reduced. So the size of the whole atom also gets reduced. This cycle goes on for several months to several years. In this way, the mass of the iron core gets increased. But as I said before, after crossing the Chandrasekhar limit, means 1.44 solar mass, the electron degeneracy pressure can't hold back. As the electron degeneracy pressure can't hold back, the inward acting gravity of the star starts dominating. Within milliseconds, the star collapses from red giant to a small ball. As it pushes the whole star inward, the electrons of the iron atom gets pushed inside the nucleus of the atom. As a result, the electron and proton are forced to fuse together and produce neutron. This reaction produces a huge amount of neutrinos, the most important particle for type 2 supernovas. These neutrinos and radiation pushes the whole star outward and makes a huge explosion, which is easily visible from millions to billions of light years. This powerful event can easily outshine the brightness of the whole galaxy. Unlike type 1a supernova, type 2 supernova doesn't destroy the core completely. The core where the neutrons are formed fusing electrons and protons stays intact. This new core is called neutron star, as it's almost completely made up of neutrons. Just for example, think an object mass equivalent to our sun is packed within a sphere of diameter only 12 miles or 20 kilometers. That's how dense a neutron star is. The story doesn't end here. If the core of the star still collapses due to its own mass, then it will create the densest object in the whole universe, the black hole. It generally forms if the mass of the original star is more than 30 to 40 solar mass. Till today, our understandings are very limited about the black holes. Still, if you want, I'll make a separate video on neutron star and black hole. From a human perspective, we see a new star in the sky, reaching its peak brightness within 3 to 9 days and dimming out throughout the time span of 4 to 6 months. The supernova of the year 1054 was a type 2 supernova. We can see the Crab Nebula and the neutron star at the center of the nebula. There are many kinds of supernovas and many subclasses of the type 2 supernovas, like type 1b, type 1c, type 2b, type 2l, type 2p, and type 2n. Here, type 1b and type 1c supernovas are almost the same as type 2 supernova, but it usually happens in the case of a Wolf-Rayet star, where the presence of hydrogen and helium is almost zero. The type 2b, p, l, n are 4 kinds of type 2 supernova according to their light emission curve. But one kind of supernova called kilonova is very unique. According to Sir Albert Einstein's general theory of relativity, if two objects with high mass orbits one another, their relative mass and speed will increase day by day, and the distance in between two objects will decrease day by day. One day, when their relative speed will exceed 60% of the speed of light, they will collide. This kind of collision is very rare in our universe, but good news, we have found it. When two super dense neutron stars left behind by their individual supernovas starts to orbit each other, they collide after a long period. This collision is called Kilonova. This explosion's luminosity is not as high as supernova, but it produces gamma ray blasts and gravitational waves. These two are the god of destructions on the universal scale. It is tough to understand the gravitational wave, especially if you don't know about the space-time curve. We will talk about it in a different video. Despite all, do you know the nova, supernova, kilonova, whatever we talked about earlier, is the only way of the formation of heavy elements around us? Whenever this astronomical explosion occurs, within milliseconds, it pushes the matters outward with such an insane pressure that the elements can't hold back its own atomic or nuclear structure. It breaks apart. After explosion, in the vacuum of space, the particle starts fusing with different particles and forms new atom and complex atomic structures. When we talk about heavier elements than iron, like gold, silver, then supernova is the only source of these elements. Next time when you will touch gold, please remember you are touching a supernova remnant. That's why the famous American astronomer Carl Sagan said, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in apple pies were made in the interiors of collapsing star. We are made of star stuff." It's very tough to realize, but it's true. That's it. Supernova, the death of a star, one of the most mysterious events in the night sky. One last question for you. How our ultimate powerhouse, the sun, will end its life? Will it go through a supernova? And if you have any specific question about this topic, please don't hesitate to write it down in the comment section. I would love to know your thoughts. If you found this cosmic journey as fascinating as I did, please give this video a thumbs up and share it with your friends and family members. And remember, keep looking up, stay curious, and explore the mysteries of the night sky.